I'm going to talk today about no carbon hydrogen as a transportation fuel. So this builds nicely on a couple of talks that were given this morning by Jack and by Inez, by Dan. What I want to talk about is the roles of looking forward toward a world where we're 80% decarbonized, and then look a little at hydrogen's role in the last 20%. But using hydrogen, as we discussed some this morning, will really require a large transition. In fact, 3 transitions: new types of vehicles, which would have to be adopted large scale on the market, new fuel infrastructure, or new sorts of uses of the existing fuel infrastructure to make this new fuel, and finally decarbonizing primary resources. And these could be happening simultaneously. In fact, the vehicle and fuel part will have to happen in pretty close lockstep in order for it to work. There'll have to be stations for vehicles and vehicles for stations. And then the decarbonizing primary resources will have to happen over time in order to get the benefits of fuel cell vehicles. I might say that the future role of hydrogen I see as rather path dependent, so it kind of depends on what we do, how we start with hydrogen, maybe as to where it goes, and also perhaps how it competes with other zero emission options like plug-in vehicles, of which there are over 1 million in the world now. And also it's geographically dependent, I think, like a lot of renewable systems, as to what resources you have and what kind of demand you have there as well. So I'm going to look at both getting from here to kind of an 80% reduction, and then look at the final 20%. Look at a world we're cutting there. So what are some characteristics we would like to see in a transport fuel for the present and for the future, for the last 20%? So it has to be something that's technically feasible and potentially cost competitive to produce and store and distribute to consumers. And it should enable attractive vehicle attributes, good vehicle performance, safe, acceptable range and refuel time. Hopefully, zero carbon emissions and zero emissions at the tailpipe are a great thing, and well-to-wheels efficiency. We'd like to rank well on other sustainability indices, such as using water and land. And we'd like it to be scalable. And by that, maybe in the context of thinking of the last 20%, there should be plentiful zero carbon primary resources it could tap into. And thinking about the whole transition from now till then, there should be some feasible infrastructure build-out strategy. How could you either leverage the existing infrastructure to try to get hydrogen to consumers, since we don't have a large hydrogen infrastructure at present? Just a couple of words where we are now with hydrogen and fuel cell vehicles. Fuel cell vehicles are being developed by automakers worldwide. There are some that are being introduced now after a period of several decades of research and development on the components, especially the fuel cells, the hydrogen storage, integrating this into vehicles. We now are demonstrating vehicles and stations together, and what I like to think of as network demos. So these are not a one-off vehicle or a one-off station to prove a concept. That was kind of been happening for the last maybe a decade or 15 years. Now we're kind of, as I see it, entering a new phase with hundreds to thousands of fuel cell vehicles and maybe tens to hundreds of stations in regional rollouts. And one of these places where this is happening is California, but we're also seeing this in Japan and in the EU in various countries as well, and also some activity in other countries such as South Korea. There has been good progress in some key technologies that have gotten us to the point where you can have kind of a workable vehicle that has an over 300-mile range and a fast refuel time, and that the car makers are putting out there. Notably, Hyundai and Toyota have introduced hundreds of vehicles into markets in the US and in Europe and in Japan, and others such as Daimler and Honda and GM, and pretty much all of them are playing in this space. And I think, as Dan brought out earlier, looking forward, the automakers have kind of a map of what the potential applications are, and they tend to see battery vehicles and fuel cell vehicles as both important for a zero-emission future. And the battery vehicles perhaps covering more of the city and the smaller car, the fuel cell vehicles, and also you could say a plug-in hybrid could play in some of this space as well, being a larger car, a longer range of fast refueling time, behaviorally kind of like what we do with our liquid fuels today. Hydrogen storage is, compressed gas is used now because it's simple, but it's still costly. There's continuing R&D on automotive PEM fuel cells as far as the fuel cell cost and the fuel cell life, and that's ongoing. Hydrogen production and delivery. Large fossil hydrogen infrastructure already exists, and it's used to produce hydrogen for chemical uses, mostly oil refining and also things like methanol and ammonia. And there is a infrastructure delivering hydrogen by truck for these kinds of applications. If all the hydrogen that was made for industrial applications were used in cars, it would probably be on the order of 30 million cars that could be fueled in the US alone. So it's actually, several percent at least, maybe 5% of the natural gas output in the country goes to make hydrogen for these purposes today. So there is this nascent, 1% scale industrial hydrogen infrastructure, and that's what we're relying on now in these initial demos, largely, as well as some on-site production, testing out electrolysis and steam methane reforming. So right now, we are kind of piggybacking on existing infrastructures. And this drawing here, and you'll have to excuse my not so great drawing, these are meant to represent sources, primary sources, wind, solar, pumped hydro, biomass, nuclear, and so on, that could be actors within a low carbon world. And then these are meant to represent end uses, cars, trucks, planes. And these are two grids that are common use. The electric grid, all of these actors could contribute to the electricity, and the natural gas grid. And here we have fossil natural gas, and also a route down here meant to portray methanation, where you would have renewable hydrogen produced electrolytically combined with CO2 from a renewable source, probably biomass, and then made into methane, which then is renewable methane with hydrogen as a feedstock, which then goes into this grid. Right now, what we're doing is taking fossil natural gas and making hydrogen out of SM in a big steam methane reformer, delivering it by truck to stations, or maybe making it at a station. Or we're using an electricity grid and doing electrolysis at a station. And that's how we're making our hydrogen right now. In the future, though, so can hydrogen do the things that we want to do as far as a fuel in the future? I would say yes, in the sense that it appears to be technically feasible to produce it and store it and distribute it to consumers, and potentially cost competitive if you scale up systems. And we do have attractive vehicle attributes, and again, there's reason to believe, I think from some credible analyses, that the cost of these vehicles could come down in mass production. Probably I'll refer you to an analysis that was done by the National Academies in 2013 called Transitions in the Light Duty Sector. And they dealt with this a lot on a lot of different types of vehicles, not just fuel cells. It was across the board, batteries and natural gas and so on. And then as far as the carbon emissions, depending on the sourcing, it appears you really could do pretty well, well to wheels, as well as hydrogen being zero emission. But what's really makes the path dependence, I think, is how we distribute this hydrogen and how it might compete with other actors in this realm. So anyway, at one point I want to just stress too is that hydrogen, and electricity also does this, it enables high vehicle efficiency as well as the option to access these vast intermittent renewable sources. So there's a twofer benefit there that you get. You can get to these zero carbon sources, and you also have a very high vehicle efficiency, on the order for fuel cells of perhaps twice that for an internal combustion engine. So that's a benefit it has over hydrocarbon fuels that are combusted in a vehicle, even if those are renewable. Now, so I'm going to talk about, and that gets to another point. Whenever you add hydrogen, use it as a feedstock and make another fuel out of it, if it's combusted, you lose that benefit of the fuel cell conversion with hydrogen. So now I'm going to talk a little about some different paths. Utilizing the existing infrastructure, we could do this in electricity, make hydrogen electrolytically either at a station or nearby and deliver it. We could leverage off the natural gas grid and use currently fossil, but maybe increasingly some renewable natural gas mixed in for hydrogen, as well as using this industrial gas system. Blending in hydrogen into the natural gas system is kind of an intriguing way to get otherwise curtailed wind power, for example, into the grid by making hydrogen. But there's some limits on this, perhaps 5 to 15% by volume, depending on the system. is you run into materials problems, potential problems with end-use systems, and so on if you get much above this. And so it might help early on, and you might get credits, things like LCFS credits or other things for adding in this renewable component to the fuel. But it's going to be a fairly limited effect on the GHG, aspects of it. Plus, if you burn the hydrogen component of a mix, then you're not getting the fuel cell efficiency benefit as well. So I think this is an early transition thing that could happen, but probably by the time we get to 80% reduction, I think it may be, we may not be doing that anymore. Just a word on methanation and other kinds of processes that combine hydrogen chemically to make a new fuel. There may be good arguments to do that in certain circumstances, but again, you will have efficiency losses every time when you do another conversion. And by the time you get up here, if you also have, in the transportation application anyway, if you have an efficiency loss due to the fact that you're in an IC car instead of a fuel cell car, those efficiency disbenefits will add up, and so you have to look at those sorts of ideas pretty carefully. So let's say you also could build a dedicated hydrogen infrastructure, and I haven't drawn that on there, and I don't know if I have any other colors here. Not picking green for any biased reasons, but you could make hydrogen electrolytically and then have a distribution system that went to hydrogen stations. And this could fuel light-duty vehicles, possibly some of the trucks, as Dan discussed. Probably be pretty difficult for aircraft, and I concur with what Jack said earlier. When we looked at this, the amount of energy flow going into an airport in San Francisco was several gigawatts. So you would need to build just huge amounts of renewable energy. If we're doing this decarbonization in the 80% already reduced world, I think it's going to be real tough. So I think the liquid fuels are going to win out there, perhaps. And so anyway, but you could build a dedicated hydrogen system, and people talk about that. And in the case, if you were really successful with getting lots of hydrogen users out there, and you had a big, dense demand, then you could build pipeline systems. And it turns out that's the least cost way once you get over a hump. I estimated something like 25 to 50% of cars in a city running on hydrogen. Then you could do the pipeline system. Before that, something else. So let me just talk now briefly about the gotchas in this and what's there. Well, one big, huge question is, will consumers adopt fuel cell vehicles if we're going up against the other zero-emission vehicle, plug-in vehicle, which will be the most attractive? Fuel cell vehicles do have a longer range. They could be bigger, faster refuel time. Will plug-in vehicles prevail in mass markets? We just don't know, and both of these are going out there, and they should both definitely get a shot. Also, this is a complex problem, and I think it's going to be regionally specific how you design or choose what to do with renewables. One thing, thinking if you're in a last 20% world, and maybe you've gone up the supply curve for your local intermittent renewables by that point. You're using a lot of them already, perhaps. And that point, the path, let's say wind to plug-in vehicle miles. So wind to miles is you get about twice as many miles with a plug-in vehicle, or maybe 1.5 times as many as you do with a fuel cell vehicle. So if you're fairly constrained on how much renewable energy you have, that could become a point as well. Okay, just to finish up, priorities for R&D, continued research on fuel cell costs for automotive and lifetime, hydrogen storage research improving on electrolysis technology. Jack covered that very well, so I won't go into details. And some actions. I think it's important to support public-private partnerships and other early commercialization actions that are happening now. The business case for hydrogen is tough. It looks like eventually it turns around and you make money, but it could take 10 years to get there. So it's hard to go to conventional financing organizations and get money for that. And according to my estimates, other people have estimated these, it might take on the order of 10 years and maybe a few $1 billion to come up to scale regionally or in several regions. And it's more than individual R&D projects, but and quite a bit more, but it's a lot less than the dollar flows in the energy system. Another key result from that NRC study in 2013 on transitions in light duty, the long-term benefits appear to really outweigh these early transition costs to get through the valley of death with this. So I'll end there, and thank you very much.